Today we're going to talk about understanding Python performance with profiling. We're going to go over what profiling is, how code executes, and then two kinds of profiling, function profiling and line profiling, and then finally close up with some tips. So first let's talk about what is profiling. Profiling is measuring how much time is spent executing different parts of a program. So you can imagine profiling is kind of like debugging. Debugging is used for checking the logic of your program by looking at how each of the parts are running and inspecting the variables. Profiling inspects time, how much time is spent in each function and each piece of your code. However, an important thing to remember about profiling is that unlike debugging, where obviously your code has to work correctly, it isn't always important that your code is fast. Sometimes programs you don't run very often. Sometimes they're programs that run fast enough on human timescales that it doesn't matter if they're 50% faster because it would go from 10 seconds to 5 seconds, and that doesn't matter for you. So it is really important to remember that profiling is only important when the time a program takes to run is important to you. Perhaps it's you have a deadline to get the results done. Maybe it's a program that you run over and over again all day, and speeding it up by 50% might let you get more work done. In those cases, profiling can be really, really important. So if you're going to profile a program, you have to make a choice about how to profile it. What inputs do you put into your program? Because you can often run it many different ways. And the most important thing to remember is that you want to profile your code running it in the configuration most like the use case that you actually want to improve. If you have a full analysis run that you want to profile, ideally that's what you would run. But if that analysis takes 2 hours, 3 hours, that's not going to be a very practical profiling case because you're going to want to run the profiling a lot. You're going to run it once to get a baseline, and then you're going to run it again after a change and run it again after another change. And if it takes 2 or 3 hours every time, it's going to be hard to make progress. So it is reasonable to slim down your input such that the program finishes maybe in 5 or 10 minutes, maybe in a few minutes. Ideally, that lets you have a turnaround that is really conducive to optimization and trying experiments and that sort of thing. However, you don't want to shrink it too much, and you definitely don't want to use your unit tests. Unit tests are usually designed with very, very small inputs in order to get easy to verify results back. And very simple sort of toy examples have a same problem. They tend to overweight the one-time setup in your code and not measure the longer iteration piece that is what typically takes up all the time. You'll be measuring the wrong piece of your program if you run a profile that's too short. So before we get into the different kinds of profiling, it's good to look at how code actually executes in Python because that will help to understand some of the terminology. So let's take an example function here. In this case, the solve function is actually performing Newton's method to find the roots of a function. It's pretty short in Python, but these lines of code are what a person writes, but they're not what the interpreter runs. What the interpreter does when it loads this code is translate it into the bytecodes you see here on the right. This is what the interpreter actually goes through. And in fact, there is a direct mapping that each line of code maps to some number of bytecodes. The first line maps into 2 bytecodes and the other one maps into 4 and so on and so forth. So when you are profiling your code, what you are measuring is how long these bytecodes take to execute in the interpreter. You can basically, you can imagine sitting there with a stopwatch and turning it on at the beginning and turning it off at the end. Now, when it depends on what is going to count for the time that solve spends, one way to count that is to look at how long the bytecodes within this function take. You'll notice that in yellow, this function calls 3 other functions. It calls the absolute value function, it calls f, and it calls df. You can either, and we'll see how this works, you can either choose to include those calls as part of the time that solve takes to run or not. And depending on what question you're asking, you may want to include the time spent in function calls or not in this function. Another way to think about the relationship between functions calling other functions is something called the call tree, which you could imagine starts at the top of your program with, say, your main function, and then has leaf nodes that are all of the functions that function calls. So main might call load and solve, and then load would call open and read, and then solve would call absolute value f and df. And so this represents, in effect, the structure of your program, and the profiling that you do is effectively assigning times to all of the parts of this tree. Now, the terminology used in the Python profiler is total time and cumulative time. Total time is the time spent running the bytecodes of just this function and excluding any of the function calls that it makes. So in this simplified example with these are made up times, we're pretending that open and read don't actually call subfunctions. In fact, they do, but we're not going to show them here. So we're going to say open takes a millisecond and read takes 5 milliseconds. When you roll that up to load might spend 2 milliseconds running its own bytecodes and then 8 milliseconds total because it includes the 6 milliseconds it took to run open and read. Similarly, solve might only take 1.5 milliseconds within the function, but when it adds up all the time that it spent calling all of ABS, F, and DF, then that adds up to 18.5 milliseconds. And so depending on the question you want to answer, if you're saying where in my program is the time being spent, you might want to look at cumulative time or total time. So let's take a look at function profiling, which we're getting pretty close to here. So there are two kinds of function profilers. One is called a tracing profiler, and this is what cprofile is and what we'll show here. And this measures every single function call to compute exact times. Now, the problem with a profiler is that the overhead of stopping at every single function call boundary to make records slows down the program, and it can sometimes slow it down quite a lot depending on how many functions are being called. So a profiler is not a good benchmarking tool because your code will always run slower and may run slower in a very nonlinear way depending on how many function calls go on. So profilers are good for comparing times within different, like you want to compare how much time is spent in one function compared to another function, but overall measuring the time of your whole program is not going to be done very accurately with a profiler. So you have to be aware of the error that's introduced by the overhead. Now, because of the slowdown of tracing profilers, people have also created what are called statistical profilers. What statistical profilers do is you can imagine that at any point in the program, you're some level deep in that call tree. Maybe you're down running DF, or maybe you're running read. And what a statistical profiler do is set a timer to basically interrupt the program at some fixed interval and look at the call stack, look at where you're executing, and then write that all down, and then do it again and again and again. And over a long enough period of time, the statistical profiler will build up an estimate of how much time you spend in each function just by taking those snapshots repeatedly. The nice part about a statistical profiler is that its accuracy can be set to whatever you want, and by lowering the accuracy, you lower the overhead substantially. The problem is that if the accuracy is too low, like for example, the sampling interval is too long, you might actually miss entire calls to functions that just never happen to show up when you snapshot. So there's a trade-off with the statistical profiler, although the low overhead operation of them makes them very appealing, especially if you want to, say, run them in production or want to be able to use them without adding extra overhead to the thing you're trying to profile. So we're going to talk about cprofile, which is a tracing profiler. In this, you can go Google around and find other kinds of profilers out there once you understand the basics. So cprofile is really nice because it's built into Python. You run a script with the cprofile module using this command here. Python-m lets you run a module as if it were a command. Usually what you want to do is profile and save it to a file. In this case, we're going to save it to stats.prof. What you want to do then is once you have the profile, you can view it with the pstats command. So in this case, Python-m pstats, and it will give you kind of a little mini command line interface, almost like a debugger, to be able to explore the results that were recorded from the profiling pass. So when you're running pstats, there are a number of commands. The most common ones you're going to use are really the first two. One is to sort and to say whenever you're going to list functions, which the next three commands will all list functions, what order do you want them sorted in? And the two orders you usually care about, although there are many, is usually do you want them sorted by cumulative time, biggest at the top, going down, or total time? Remember, cumulative includes all the function calls. Total time only counts time spent in the function itself, not in the subfunctions. And once you pick that, that's remembered for all subsequent requests until you change it again. So you could type sort and cumulative and hit enter. And then if you want to then look at just a list of all the functions in the code and see how long things took, stats will show you those. And you can do stats and a number to see the top 25 functions or the top 50 functions. And then sometimes it's useful to pick a place in the call tree and say, I want to see the stats for every function called by a given function name, or all the things that call this function. You can kind of either look up the tree or look down the tree. And these sorts of exploratory tools will help you understand both where the time is spent and why. Like, is a function slow because it calls a lot of slow functions, or because itself is doing a lot of calculation? And then finally, you can take that same profile file and visualize it with a tool like SnakeViz. So here's a screenshot. We'll see in a short bit of an interactive demo, but SnakeViz is really handy for showing you how the time is spent in the call tree. You can imagine that the depth from the top down is sort of how deep into the call tree are you. And then you can very quickly see by the width which functions take up the most time, and then there are various options to filter and drill down and that sort of thing. So here in the notebook, we're going to take a look at function profiling first. So notebooks are a great way, if you can, to do profiling because they let you experiment quickly. You can even make notes in the notebook about the results you're seeing to remind yourself later when you pick things up. So let's start by defining that same function we saw in the slides, solve function. And then here we're going to pass in two functions. Now, to make things interesting, we're going to introduce an artificial delay because normally this would run extremely quickly. So in f of x, I'm inserting a for loop that wastes some time. And in df, I am running another for loop that wastes some time that takes twice as long as the one in f of x. So df is a slower function than f. And in case we just want to see what these functions look like here, here's our little wavy function that intersects the zero line at many points. And if we were to say seed with a particular value, it would find the zero over here at about 3.25. So when you're in the notebook and you want to run the profiler in the notebook, so we saw how to run it from the command line, you can use the magic command that starts with a percent called prun. What prun will do is it'll run the profiler. You can tell it what you want to sort by, in this case, total time. And you can also save the output. In this case, we're going to save it to solve.prof. And then everything after this point is the Python statement you want to run and record all of the profiling for. So we're going to run solve here with these arguments. When we do that, a box pops up here in Jupyter that shows you the results from this thing sorted by total time. You can see the highest total times at the top. And as we expect, because we put in that delay, df is the slowest function. And most of the time is spent in df, and about half as much time, which is about right, is spent in f. And then solve itself is actually pretty small. This exec is just the time actually it takes to parse the code we wrote here, this solve df. The exec function is being used to parse that. That actually takes more time than solve itself. Remember, that was total time. Now, inspecting by text is sometimes a little bit hard, so if we want to run SnakeViz, I find it useful to actually run SnakeViz as a subcommand. So if you in Jupyter start with an exclamation point, this sends this to the shell. So in this case, bash, since I'm on a Mac. And so this will run the SnakeViz command with this recorded profile that we saved up here. So let's do that. And what that will do is open a new tab in my browser, which shows me the results here. And now we can see the exec, and this stuff is just sort of overhead. Here's the actual solve function that takes this amount of time. Most of that time is spent in df and f, and there is a tiny sliver you can't quite see. It's actually less than a pixel wide. That would have been the time spent running the bytecodes of solve itself. Because solve runs so fast, almost all of the time is spent in these subfunctions of df and f. So now let's talk about line profiling. Line profiling is different than function profiling because you only line profile important functions. Function profiling, you record the whole program. Every function that's called gets written out to that profile trace. Line profiling, because it is so much, there's so much more overhead because there is accounting being done on every single line in the function, not just every function call. You can't really afford to line profile every function in your code. Also, that would be an overwhelming amount of information. So usually you want to zero in on a couple of functions that are really critical, and those are the ones you line profile. And line profiling is useful when you're dealing with what I would call sort of an algorithm-heavy function. Maybe it's a little longer function, maybe it's 20 or 30 lines, there's a lot of branching or looping, or you're using some sort of heavyweight functions like NumPy functions. It's very hard when you're just looking at code to look at a NumPy function and guess how long it's going to take. Because that function might work on arrays of different dimensions, It might have some kind of more iterative algorithm, or it might be very simple. So NumPy is very good at making your code readable, but it doesn't give you any visual clues about how long things take. And so line profiling, a piece of code that uses NumPy a lot, is hugely helpful. So if you want to do line profiling does not come with Python. You have to install something. And then in this case, using Anaconda, you can conda install line profiler. And then what you can do if you're doing this from the command line is you can decorate your function with the profile decorator. Just put it up above the def for the function you want to look at. And then you run the script, the kernprof command. And this will print the results to the console. Now, the thing to note is that the way this works, kernprof is actually putting a profile function into the built-ins of Python when it runs, so that your profile decorator will actually work. If you put this in your program and just run it normally, you just run my script without kernprof, you would get a error because profile is not defined. It's not defined in the built-ins by default. So you will want to put in profile, run with kernprof, and then take it out or comment it out temporarily. So there are tricks you can do to allow you to just leave the profile in and have it have no effect when you're not running kernprof, but that's outside the scope of this thing. So the results here will print to the console, and we'll see what those look like in a bit. All right, so let's do some line profiling. So here in the notebook, we're going to use a more interesting function than the one that we had before, because the one we had before was a little too simple. This one has some NumPy calls in it. So if you remember your physics, what we're actually doing here is computing the electric potential created by a collection of point charges. If you don't remember physics, that's okay. Don't worry about what this function's for. It's just doing some NumPy though. In this case, the function is taking in a 2D array n by 3 and another 2D array m by 3, so n and m don't have to be the same. And then we're doing some access tricks here in order to basically take the difference between all combinations of those point charges. And then we're going to take those distance vectors and find their scalar distances. So we're going to do some math. We're going to square things. We're going to reduce along an axis, and we're going to take the square root. And then finally, we're going to take the reciprocal, do another sum, and return this 1D array. So this is doing some significant, potentially, NumPy calls. So this is what we're going to measure. Now, to actually test it out, just to give you an idea that, make sure it works again, you want to make sure your function runs before you try profiling. These helper functions generate some test data. We're going to generate 15 sample points and 50 charges that we're going to compute with. And then if we just want to see what this looks like, we're basically measuring the electric potential along these red dots caused by the charges in the circle, in this case. Now, this isn't very much, so to make things more interesting, we're going to increase the data size. So if we were doing this maybe in some other application, maybe we want to measure the potential at 1,000 points caused by 2,000 charges. So this is actually, this call here is the one we're going to be measuring. So if we want to run the line profiler in the notebook, we have to first load an extension. Again, line profiler is not built into Python, so when you install the line profiler, this Jupyter extension is made available, but it's not activated until you run this load ext line profiler. What this does is this adds a new command called lprun. So remember, function profiling was prun, lprun is line profiling. And so in this case, if you want to run this now at the command line, before we talked about using the profile decorator, here when you do lprun, you can pass this -f, which just says the compute potential function, which is the one that's of interest to us, that's the one I want to line profile. So you don't have to go modify your code or something like that. You can just indicate the name of the function that you want to profile. And then everything at this point is the Python statement that's going to be executed to generate the profiling data. So we're going to do that compute potential of many points and many charges. And when we run this, we get the same kind of thing we got with cprofile. It pops up this box that we can look through. The difference here is that, let me shrink down the font a little bit, is that it shows, instead of function calls, it shows line by line on compute potential. And the nice thing about it is that while it shows these absolute values here, it's really handy. It'll compute a percentage. So it'll normalize this to 100% and say, okay, 35% of your time is spent computing those distance vectors, but almost 60% of your time is spent computing those distances. And so this is where if you are trying to speed things up or just understand where in your code the time is being spent, this immediately helps you zero in on this line as being the culprit. That if you want to have the biggest impact, you should see what you can do about this line more than other lines. Now, maybe there's nothing you can do here, but for example, maybe you switch to some numba or something like that to do this computation. In fact, you could convert this whole function to numba to speed it up. But at least you know where to look. For example, you could immediately see that this function is not very important. So time spent trying to figure out how to do this more quickly is not really going to be very productive. And there you go. This has been a quick introduction to profiling. So remember, when you go try this out yourself, one, don't profile code before you know it works. The last thing you want to be doing is debugging incorrect code, or worse, measuring the time that code that doesn't work or doesn't give you the right answer takes. You want to profile with the most realistic inputs you can, but you want to complete in a reasonable time. Best target you can is if it's done in sort of 2 to 10 minutes. That'll give you the best turnaround time, but obviously if you have to go longer, you have to go longer. A good place to start with a program is to start with function profiling to find out what the important functions are. And here I think cprofile and snakeviz are really nice tools in order to be able to find those critical sections in your code where the most of the time is being spent. And then when you find those functions, it's useful to switch to line profiling in order to understand the time being taken by those handful of very critical functions. So that's it. Good luck on your profiling.